Have you ever actually looked down at the ground and wondered what is really going on thousands of miles right beneath your shoes? It's kind of wild to think about, right? I mean, we've mapped distant stars, we've sent probes to the very edge of our solar system, yet the deep interior of our own planet remains one of the most mysterious, fiery, and totally inaccessible frontiers known to science. Welcome to this explainer, where we are going to unlock the incredible mystery of the hidden world beneath our feet. We're going to use some genuinely fascinating scientific clues to journey straight into the deep.
All right, let's take a quick look at our roadmap. We'll start with investigating Earth's hidden depths, move into decoding Earth's seismic waves, take a journey inside Earth's layers, look at minerals and rock types, and wrap up with the endless rock cycle. Essentially, we're charting a path from the surface, dropping straight down to the searing hot core, and then coming all the way back up again.
So, let's kick things off with Section 1, Investigating Earth's Hidden Depths, or the Ultimate Mystery.
Now this brings up a rather frustrating problem for geologists. How do we actually know what's down there? Unlike a melon that you can just slice open to see the seeds, we can't exactly just dig a hole to the center of the Earth. Our direct sources of information are incredibly limited. Deep ocean drilling, shallow mining, they barely even scratch the surface. And yeah, volcanoes kindly bring up magma from below, but they only show us a tiny fraction of the upper layers. We're essentially flying blind here, which turns this into a true geological detective story.
Since we can't physically go down there, scientists have to be clever. They use indirect clues to piece this massive puzzle together. For instance, we know temperature and pressure spike the deeper you go. In fact, the temperature rises about 1 degree Celsius for every 32 meters of depth. We also look at gravity anomalies, because gravity actually changes depending on how heavy the mass of rock is directly below you. Add in magnetic surveys from the Earth's spinning center, and we get an even clearer picture. We even look to space. Seriously. Meteorites formed around the same time as our solar system, so checking out their composition is basically like looking into a mirror of the Earth's own deep, heavy materials.
Moving right along to Section 2, Decoding Earth's Seismic Waves, which acts as our planetary sonar.
This is absolutely our most powerful investigative tool. When an earthquake strikes, it acts like a massive planetary X-ray, sending energy waves echoing completely through the Earth. We classify these body waves into two main types, P waves and S waves. P waves, or primary waves, are fast, longitudinal, and they can plow through absolutely anything, solids, liquids, gases, you name it. But S waves, or secondary waves, are a bit more finicky. They're transverse shear waves, and they have one massive weakness. They can only travel through solids, and this is a real game changer. Because S waves completely disappear at certain depths, they give away the massive secret that a huge chunk of our planet's interior is totally liquid.
Because these seismic waves change velocity and direction, meaning they refract. When they hit materials of different densities, we end up with what are called shadow zones. Imagine them as massive blind spots on the opposite side of the Earth from an earthquake, where seismographs just suddenly go totally dead. P waves get bent and vanish between 103 and 142 degrees away from the quake's focus. But even more amazingly, S waves vanish completely beyond 103 degrees. No trace of them at all. They literally hit the liquid outer core and just stop dead in their tracks.
And that brings us perfectly to Section 3, Journey Inside Earth's Layers, Descending into the Deep.
Okay, using all of that incredibly precise seismic data, we can take a structured descent straight down. And it is truly staggering to realize just how insignificantly thin our crust actually is. The crust, the place where every human being has ever lived, built cities, fought wars, makes up just 1 measly % of the Earth's total volume. Below us is the massive mantle, claiming 83% of the planet, and finally, the dense core making up the last 16%. We are quite literally living on the ultra-thin skin of an apple.
Let's look a little closer at those outer two layers. The solid, rigid crust goes down anywhere from 0 to 70 kilometers. It has a lighter top layer called sial, made of silica and aluminum, and a much denser bottom layer called sima, silica and magnesium. Beneath that delicate crust lies the gargantuan mantle, extending 2,900 kilometers deep. The mantle is absolutely packed with dense, heavy materials, and its upper portion, the asthenosphere, is so intensely hot that the rocks behave like a thick, viscous fluid. Actually, it's the convection currents rolling around in this hot magma that cause our solid crust to float and shift around on the surface in the first place.
Now, as we travel deeper, the physical properties of the Earth don't just gradually blend together. They snap abruptly at borders known as discontinuities.
First, we pass the Conrad discontinuity within the crust. Then we hit the famous moho, where the crust violently transitions right into the mantle. Deeper down lies the Rapeti. Then the Gutenberg, which marks the terrifying boundary of the fiery outer core. And finally, the Lehman discontinuity, separating the outer and inner core.
Speaking of the core, let's plunge all the way to the center. While it's only 16% of the Earth's volume, it accounts for a whopping 32% of its entire mass. Why? Because it is incredibly dense. It's mostly composed of heavy metals, specifically nickel and iron, a combo scientists cleverly call knife. We know from our S-wave shadow zones that the outer core is a swirling, chaotic ocean of molten liquid metal. But here is the mind-bending paradox. As you cross into the inner core, the materials become entirely solid. Wait, how is it solid if it's even hotter than the liquid above it? Well, it's simply due to the crushing, unimaginable pressure from the entire weight of the planet pushing down on it, physically forcing the melting atoms to lock into a solid state.
And when I say it's hot down there, I mean it is an absolute inferno. The inner core sits at a staggering 7,000 Kelvin. To put that completely wild number into perspective, that is actually hotter than the surface of the sun, and it's sitting right here in the center of our own planet. No way, right?
Whew. Okay, let's take a breath and travel rapidly back up to the surface for Section 4, Minerals and Rock Types, the tangible evidence.
Back up here in the fresh air, we can examine the physical evidence left behind by all those massive underground forces. The materials that make up the crust we walk on every day are fundamentally built of minerals. And remarkably, just two elements, oxygen and silicon, account for 75% of the crust's entire weight. These elements combine to form the major foundational minerals of our world. Get this, feldspar alone makes up half of the entire Earth's crust. You've also got quartz, which makes up a ton of our sand, alongside pyroxene, amphibole, mica, and olivine. These are quite literally nature's building blocks.
So, the crucial takeaway here is that rocks are quite simply mixtures of these minerals, and because they don't have a strict, definite chemical composition, we categorize them purely based on the violent or gradual ways they were formed. Igneous rocks, like granite or basalt, are born from heat. They are literally just cooled down magma. Sedimentary rocks, like sandstone, are the result of weathering. Wind and water break down older rocks and compress those tiny fragments into horizontal layers over a very long time. Finally, metamorphic rocks are the shapeshifters of the group. They happen when existing rocks are dragged back down near the mantle and subjected to tremendous heat and pressure, fundamentally altering their hardness and texture.
Which perfectly leads us into our final section, the endless rock cycle, the Earth's very own recycling machine. You see, the Earth is not just a cold, static lump of stone floating through space. It is a living, breathing, planetary recycling machine. And this entire recycling system is powered by an eternal tug-of-war between two massive energy sources. On the outside, you have solar energy from the sun, which drives our weather, wind, rain, and ice, constantly eroding and breaking down the surface. But on the inside, you have that intense internal Earth heat, that 7,000 Kelvin battery in the core, driving the massive tectonic plates, causing eruptions and melting rock from below.
Because of these twin engines constantly running, rocks are in dynamic, continuous motion, locked in a massive cycle that takes millions of years to complete. Here's how it flows. Hot magma rises up and cools into solid igneous rock. Then, rain and wind batter that rock, breaking it into tiny pieces that wash into the sea, eventually compacting into sedimentary rock. Over ages, tectonic forces might push that sedimentary layer deep underground, where insane heat and pressure bake it into metamorphic rock. Push it down just a bit further and it melts completely, becoming magma once again, ready to erupt and start the entire endless loop over again.
It really changes how you view the ground beneath your feet, doesn't it? Every single rock you see out there is just pausing halfway through a multi-million-year transformation, which leaves us with this final thought to chew on. If the entirety of human history, every triumph, every discovery, every single thing we've ever known has unfolded on just that 1% of the Earth's volume, that paper-thin crust, what other incredible secrets are still waiting, perfectly preserved in the fiery, unexplored depths below? Thanks so much for joining me on this explainer, and remember, keep questioning the world around you.